Hello everyone, my name is Sakib Hassan Himel and my ID is 24215-327. Today we are going to delve into the fundamentals of basic graph. This presentation will serve as a foundation for understanding one of the most powerful and versatile tools in discrete mathematics. We will cover what graphs are, explore their different types and properties, and see how they are used to model real world problems in fields ranging from computer science to sociology. Whether you are new to the topic or need a refresher, this overview will provide the essential concepts you need. Let's start with the big picture. Graphs are not just charts and plots. In discrete mathematics, a graph is a specific structure used to model pairwise relationships. The power of graph theory lies in its simplicity and abstraction. By reducing complex systems to points and connections, we can analyze and solve problems related to networking, connectivity, flow, and optimization. It's a fundamental concept that forms the backbone of more advanced topics in computer science, operation research, and beyond. So, what exactly is a graph? Formally, a graph is defined by two sets. First, a set of vertices, also called nodes, which are the fundamental units or points. And second, a set of edges, which are the lines that connect pairs of these vertices. This simple structure of dots and lines is which we use for modeling relationships. For example, vertices could represent people, edges could represent friendships, or vertices could be network routers and edges in the physical connections between them. Graphs come in many varieties. The most basic is a simple graph. It has no loops, meaning an edge connecting a vertex to itself and no multiple edges between the same pair of vertices. A complete graph takes connectivity to the maximum. In a complete graph, every distinct pair of vertices is connected by a unique edge. Now let's add more detail. In a directed graph or digraph, edges have a direction indicated by an arrow. This represents asymmetric relationships like one-way streets in a city map or followers on social media. Just because I follow you doesn't mean you follow me back. In a weighted graph, we assign a numerical value or weight to each edge. This could represent the cost, distance, time, or capacity of a connection. This is crucial for finding the shortest path in a GPS or the most efficient data route across a network. To talk about graphs effectively, we need a common language, a vertex, a single point or node in the graph, an edge, the link connecting two vertices, the degree of a vertex, the number of edges incident to it. In a social network, this would be a person's number of friends, and a path, a sequence of edges that allows you to travel from one vertex to another. Analyzing the paths help us understand connectivity and distance within a graph. So graphs can have important structural properties. A connected graph is one where there is a path between every pair of vertices. If you can't get from one vertex to another, the graph is disconnected. An acyclic graph is one that contains no cycles, that is, no closed loops. A special kind of acyclic graph is a tree, which is connected graph with no cycles. Trees are incredibly important in data structures and network design. Two other key properties are bipartite and planar. A bipartite graph is one whose vertices can be divided into two distinct sets, such that every edge connects a vertex from one set to a vertex from the other set. There are no edges within the same set. This is perfect for modeling relationships between two different types of things like job applicants and open positions. A planar graph is one that can be drawn on a plane without any of its edges crossing. This is important in circuit board design and map making, where avoiding crossings is often essential. How do we work with graphs in practice? We represent them computationally. One common way is an adjacency matrix. This is a square matrix where a 1 indicates an edge between two vertices and a 0 indicates no edge. It's great for quickly checking if a connection exists. Of course, the visual representation, the simple drawing of dots and lines, is often the first and most intuitive way we can understand the graph structure. For graphs with many vertices but few edges, an adjacency matrix can be inefficient because it uses a lot of space to store zeros. An adjacency list solves this by storing for each vertex a list of the vertices it is connected to. It's much more space efficient for sparse graphs. Similarly, an edge list is simply a list of all the edges represented as pairs of vertices. This is very straightforward, though sometimes less query efficient way to store graph data. The true value of graph theory is revealed in its vast number of applications. Its ability to model relationships and connections makes it indispensable across disciplines. In computer networks, graphs model network topology for efficient data routing. In scheduling, graphs help with task sequencing and resource allocations, like assigning classes to the rooms without conflicts. Social networks are perhaps the most famous example, using graphs to model friendships, influence, and information flow. And in geographic information systems, graphs form the basis of road networks for navigation and logistics. In conclusion, graphs are a profoundly important concept in discrete mathematics. Understanding the basics, the types, terminology, properties, and the representations provides a critical toolkit for modeling and solving complex real-world problems. The study of graph theory is a continuous journey, leading to a deeper insights into the connectivity, complexity, and optimization. I encourage you to explore this topic further. Thank you.